Okay, hello everyone. My name is Nick DiOrio. I'm an engineer at NREL, and I will be giving the presentation this afternoon on how to model a photovoltaic battery system in SAM. And so I think we're going to go ahead and get started and let the last few people joining just get set up. So an outline of what we're going to cover today. So I'm going to give you an overview of SAM's battery modeling capabilities. So kind of what systems you can model, what value streams you can look at, and where you can really start to do some worthwhile analysis in SAM. We're going to set up a battery system, kind of designing it, going through the steps that it takes in SAM to set it up, and then looking at how you would set up the dispatch strategy, how you would download the electricity rate that you're interested in. We're going to look at an optimal sizing approach for a battery system in SAM. And then we're going to, throughout the process, kind of look at what results SAM offers you to look at and kind of how you would interpret those. And so, just to give you a little background on myself, I'm an engineer on the SAM team. I've worked on the SAM team a couple years, primarily doing battery modeling. And so I have a lot of interest in this area, and it's obviously a very dynamic and growing field. SAM doesn't cover all of the interests in batteries right now, but we are trying to keep up with the most kind of the hottest topics and the things that we see as the most value. And so if you have any questions, feel free to type them in the questions box, and my colleagues will do the best they can to keep up with them. And then I will also allow hopefully about 10 minutes, maybe 10 or 15 minutes at the end to kind of address any other questions and give people a chance to ask any more questions. Just to give you a little background on SAM in case you're not familiar. It's a system advisor model. It's free software that NREL develops, and we provide it. You combine detailed performance and financial models to estimate the cost of energy for systems. It's available across all platforms, and we release 1 or 2 versions a year with more frequent patches. We also have a software development kit, which is a really powerful tool for people to access the models of SAM programmatically. And then finally, we have a pretty extensive support system, both through the built-in help system. We provide a lot of reports and documents on our website. We have an online forum, and then you can also contact us via the website. And with that, I will just go ahead and jump into the battery model and a little bit of overview of what you can do in SAM. So the battery model in SAM is a techno-economic model. We currently have it implemented for behind-the-meter storage, and so that would apply for kind of residential, commercial, and third-party ownership scenarios. Anywhere where there's a customer behind the meter consuming electricity and paying the utility. Within the battery model, you can model lead acid and lithium ion battery chemistries. So we actually have some different chemistry response models based upon the chemistry that you choose. You can perform system lifetime analysis, which is really important for battery systems because as you use them, they cycle at different depths of discharge, and those cycles affect the battery lifetime, the battery capacity, and ultimately are going to influence your capital costs as you have to replace them. And so it's important to be able to look at kind of a holistic analysis of the system. We provide detailed models for terminal voltage, capacity, temperature, and then we also have multiple dispatch controllers available to try and allow you the flexibility to model different kinds of value streams, different ways to get value out of your battery system. And I'll be walking through all of these in a little more detail as we go on. So as I mentioned, SAM is currently set up to do behind-the-meter storage analysis. And so I just want to spend a few minutes and look at what kind of value streams could a battery provide behind the meter. And so starting from the left, we have PV self-consumption. And so basically here, the idea is there might be certain situations where you want to try and locally consume as much of the PV power that you produce as possible. And the reason for that could be that you're trying to capture a federal incentive on your battery system. Those incentives typically require that you charge the battery a certain percent from the PV array. And then there are also policy issues where you might live in an area where net energy metering policies are changing such that selling excess PV generation back to the grid is no longer as lucrative as it once was. And so these could all be reasons to install a storage system to store some of that PV power during times of peak production and then use them later on. Moving to the middle, we have time of use optimization. So this is a classic buy low, sell high kind of approach where you are basically charging the battery from the grid when power is cheap and then discharging during high time of use rates. And by performing that arbitrage, the idea would be that you could extract enough value to justify the capital cost of the system. In my analysis experience, that value stream alone is typically not going to be enough to justify a battery system. However, perhaps when coupled with the option on the right, which is demand charge reduction, the possibilities become more apparent. And so demand charge reduction would be the concept of taking your peak power over a monthly period and then shaving some of that peak throughout the month in order to reduce high time of use demand charges. And so that would typically be more available for commercial utility rate structures. There are some, I believe there are some residential rate structures that are starting to get these features in them, but typically larger scale buildings have these rates. And so those are a few of the value streams that we're going to look at. I also want to point out that there are various other ancillary service markets out there that you may be able to either bid into or participate in at this scale. However, we currently do not have the capability in SAM to model these explicitly. And so I think the best way to go through the battery model and illustrate how to use it is to do a case study in which we'll set up SAM and do some analysis. And so I want to look at evaluating the economics of installing a PV-coupled battery system primarily for demand charge reduction. And we're going to look at Los Angeles, California, at a commercial building with roughly 170 kilowatts of peak demand. And we're going to be assuming that we are operating under Southern California Edison's time of use GS2 option B rate, which is a time of use rate that has both time of use energy and demand charges. The system that I want to look at would be to model a battery that is similar to the Tesla Powerwall. We're not going to model the Powerwall directly, but I think it's a good starting point since they have some publicly available specs that we can go ahead and incorporate into SAM. And so we're going to be looking at a lithium-ion nickel manganese cobalt battery. We're going to make some assumptions about the capacity of the battery. Basically, we're going to assume that we can cycle it 80% of its full capacity, and then we also want to oversize it a little bit with the assumption that it's going to degrade over time. And so we're going to assume that each battery unit that we install is roughly 10 kilowatt hours and has a nominal voltage of about 350 volts. And so with that, I'm going to go ahead and open up SAM. And please note that I'm working off of version 2016.3.14, and so that was the last major release of SAM, and there are several patches that have also been incorporated into that version. I just want to point out, while I have this landing page open, that we typically put announcements here about webinars and other kind of outreach events that we have. And so last week, my colleague Aaron Dobos gave a comprehensive webinar on how to model a residential PV system. And so that webinar is available on the SAM videos page. And then I also want to point out that we have bi-weekly half-hour webinars where anyone can join and ask questions to the SAM team in a fairly informal environment. And so if you have really, a question that you need to get answered that you haven't been able to get answered, it's a good time to do that. And so to get started with a battery project, we're going to start a new project. And the battery models live under the photovoltaic detailed technology. And as I've mentioned a couple times, they're only within the behind-the-meter space, so residential, commercial, and third-party ownership. So I'll go ahead and click the commercial financial model and click OK. And so this brings up the case that we want to start building. And so some of the first things that we're going to want to do are to specify the resource, basically, to begin the modeling process. And so we have various ways that you can get weather data into SAM. We have this connection with the NREL National Solar Radiation Database. You can download anywhere in North America, as well as various other places around the world. Or you can use the included library of TMY files that we provide around the US, and we have some international sites as well. Or you can also create your own weather file and then specify it. And that, for battery analysis, it's typically going to be valuable to have data that is at 15-minute resolution, simply because demand charges are typically evaluated on a 15-minute basis. And so if you want a really robust analysis, you want both your electric load and weather to be at that interval. Today, though, we're just going to keep it a little simpler than that and use the library TMY2 file for Los Angeles. And as I mentioned, the electric load is also a very important piece of any battery analysis. Basically, you need to have a good idea of what the demand is throughout the day, because a battery's value is derived from offsetting electricity and demand costs. And so if you really want to get a good picture of what value your system is going to add, you need to understand your electric load. And so, as I mentioned, we're going to be looking at a commercial building that is roughly 170 kilowatts of peak demand. And so I'm just going to go ahead and scale the default load profile that SAM provides. But you can also input your data here. You can change the time step anywhere from 60 to 1 minute. And we can go ahead and take a quick look at the electric load that we're going to be dealing with. And so you can see kind of a typical day here has a spike in the morning and then a spike in the evening. And so we'll see whether a battery system makes sense for this type of load profile and what kind of value we can get. So now that we've looked at the electric load and the location and resource, let's go ahead and just step through some of these other pages. I'm not going to be spending a ton of time on these other details. I just want to point out that this is where they would be. So you can select your PV module type on the module page. I'm going to go ahead and just keep it at the default module. Similarly, for the inverter page, you can select from a library of inverters. And again, I will just leave it at the default value. The system design page is where you begin to specify how you want to lay out your system, both the system size, the subarrays, the tilts, things that define the layout of your system. So to start with, I'd like to just start with a 50 kilowatt PV array. We'll go ahead and leave the DC to AC ratio at about 1.1. We'll go ahead and leave some of these other details alone. We'll just assume that they're fixed axis systems with a 30-degree tilt facing south. If you have comprehensive shading information, you can enter that here. You can do both 3D shading, you can look at self-shading, and then you can also look at snow losses. We're going to go ahead and just leave all of those alone for right now. If you have additional losses, we have some defaults for kind of these single point efficiency losses that account for things like module mismatch and soiling. But I'm just going to go ahead and leave the defaults alone for those right now. As I mentioned, it's valuable when doing a battery analysis to be able to actually do a simulation over the entire analysis period, because that's really going to give us the information about cycling and battery degradation that's going to inform our replacement schedule and our project economics. So I changed this tab on the lifetime page from PV simulation over 1 year, which would basically just run the simulation over 1 year and then extrapolate those results over 25 years into this PV simulation over analysis period, which is actually going to run the models every single time step over the 25 years that we'll be looking at. Before I jump into the battery storage page, just point out the system costs. So the battery bank costs right now by default are set at $600 per kilowatt hour. And so that would wrap up the cost of the power electronics as well. So we don't have a separate input for battery power electronics. So right now you have to simply roll them up into $1 per kilowatt hour cost. You would enter your default financial parameters. I want to point out the incentives page because for California in particular, which I believe still has the self-generation incentive program, SCHIP, you could enter information about battery incentives on this page. I believe the last time I looked at that incentive, it was roughly $1.31 per watt. And so what you could do is take the amount of kilowatts that you are looking to install for your battery and then apply that incentive, and then you would enter it basically in one of these dollar incentives here. And so that gives you kind of flexibility to look at how those incentives will affect your financing. So now onto the main page that we're interested in, which is the battery storage page. So on the top here, we want to click and enable the battery. And this is going to give us all the information that we need to specify the battery. And so, as I mentioned, we're going to be looking at batteries with an increment of 10 kilowatt hours. And so if we just assume that we're going to install one of those to start, 10 kilowatt hours and 350 volts. In this drop down for chemistry, you can see that there's various options for lead acid and lithium ion chemistries. And so if we changed these chemistries, it would replace the inputs with the default values for this battery type. And so it's a convenient way if you don't really have much information about your battery, but you do know that you have a certain type of lithium ion or lead acid battery. It's a good way to just enter the defaults. And so we're not going to mess around with this voltage curve. It's basically just a curve of how the terminal voltage varies with depth of discharge. And so basically at very low depths of discharge, you start to lose potential across the battery in an exponential response. Another important input would be the max C rate of charge and discharge. And these are simply just ways to scale the battery power. And so if we have a 10 kilowatt hour battery, a C rate of 1 means that we can discharge that full 10 kilowatt hours in 1 hour for a nominal power of about 10 kilowatts. And so if we change that to 2, that's going to mean that we can discharge that 10 kilowatt hours in half an hour. And so that would be a 20 kilowatt battery. In the case that we're looking at, we're actually looking for a power of about 3 kilowatts, or 3.5 kilowatts. And so we're going to take that 10 and if we want a 3.5 kilowatt system, that's going to be about 2 or 3 hours of battery. And so we're going to change this to 0.33. And that basically just means that we have a 3-hour battery now. So we can discharge that 10 kilowatt hours over 3 hours. We're not going to change any other properties about the cell. Okay, so right now SAM has assumed that your system configuration is such that you are connecting the battery on the AC bus. And so basically what this means is that your PV power is inverted and placed on the AC bus, and then similarly your battery is placed on the AC bus with a microinverter that takes power from the AC bus, converts it to DC, charges the battery, and then when your battery discharges, it also has to be inverted and to put back on the bus. And so this is one type of system configuration. Another popular one would be a DC connected configuration where the battery is placed basically in conjunction with the PV array with the charge controller between them, such that the PV power can be directly used to charge the battery without having to incur the loss to AC. And so we don't currently have that configuration modeled, but you can approximate it still with our current setup. You just might have slightly different losses. So right now we just have an AC to DC conversion efficiency loss and a DC to AC conversion efficiency loss from the battery to the AC bus. And so I'm going to change these to 95% for each. And I just want to point out that in an upcoming version of SAM, we will be extending the configuration options for the battery system. So then we get down into the storage dispatch controller, which I'm going to go ahead and scroll over really quick just to show you some of the other input options before we dive into the dispatch. And so if you know the cycling behavior of the battery and how it degrades with cycle numbers and depth of discharge, you can input that here, or you can use the default values that we provide. Perhaps one of the most important pieces of the economics of your system will be the choices that you decide to make regarding battery bank replacement. So right now we have it set for no replacements, and that basically means that over time, as the battery cycles and degrades, we're not going to worry about replacing the battery. We're just going to assume that the loss in capacity is acceptable. If we wanted to replace it at a certain capacity, we could specify the capacity that we want to replace it at. So for instance, if the total charge that the battery can hold is now only 20% of the original max, then we would replace it. And finally, if you want to replace at a specified schedule, you can specify that option and then tell the model exactly which years you want to do a battery bank replacement. And you can also specify the replacement cost and whether that cost escalates or de-escalates over time. And so for now, let's just go ahead and select no replacements and see how that looks. And then finally here we have thermal behavior. And so battery capacity is a function of temperature. And so you can look at how the capacity of the battery changes as the temperature changes. It's not a critical part of the model, but I think it can be interesting to look at. And so now I want to look at the storage dispatch controller, which is going to be one of the key components of our analysis. So within the storage dispatch controller, we have several different models available. We have a model that is targeted for peak shaving, and we do a one-day look ahead on the PV production and the electric load in order to program the battery to reduce power over that 24 hours as much as possible. And so I'd like to point out that it's not actually performing a cost optimization, but rather assuming that it's beneficial to reduce peak power as much as possible. And so there are some additional options that we will eventually be looking at adding for that. If you want a slightly more realistic peak shaving control, we have a one-day look behind, which basically assumes that your PV production and load will be exactly what they were yesterday. If you're trying to maintain a certain grid power, so for instance, if the line only supports 100 kilowatts, then you can program the battery to always try and keep the the grid power being purchased below that threshold. And then finally, there's this manual dispatch control, which allows you to tailor when the battery is allowed to be charged from PV, when it's allowed to be charged from the grid, how much it's allowed to be charged from the grid, when it's allowed to be discharged, and then how much it's allowed to be discharged. And you can also specify within this control whether the PV power is prioritized to meet the electric load before charging the battery, or if the PV is prioritized to charge the battery before meeting the electric load. And so that gives you the flexibility to look at a few different self-consumption scenarios. And so before we program this, we're actually going to need to program the electricity rate. And so let me do that here. And so basically on the electricity rates page, we're going to want to input that Southern California Edison time of use rate. Fortunately, we don't have to do it by hand. We can use this OpenEI utility rate database connection. And so if I type in Southern California Edison, I get a list of the commercial rates. I was interested in time of use GS2 option B. Click download and apply. And then it populates this electricity rate for me. So let's just take a quick look at this rate. So we have a fairly complex time of use rate. So this is the energy rate during the week. We can see period 5 is the peak summer time, and the rate there is about 10.2 cents per kilowatt hour. And then at the lowest time, it's roughly 5 cents. And so actually not really a large difference there. What's really the main driver of this rate for battery analysis would probably be these time of use demand charges. And so over that peak summer period, we're seeing a time of use demand charge of $15.42 per kilowatt. And so if we have a peak load of roughly 170 kilowatts, you can see how that starts to add up pretty quick. And then there's also a flat monthly demand charge of $15.44. And so this time of use demand component adds on to that flat demand component. And so we're going to see if the battery can provide value in reducing some of these demand charges. So if we go back to the battery storage page and look again at our dispatch control, let's go ahead and see if it makes sense to try and manually dispatch the battery to reduce peak demand. And so if we want to charge the battery during times of low energy prices, we could charge it in the first 4 hours of the day by specifying this period 2, which is set to charge from the grid. And then this percent capacity allows us to specify how much of the battery capacity to charge over each time step. And so we'll charge 25% per hour over these 4 hours, and that will basically make it so we're not ever charging the battery just very rapidly in one time step. As we saw before, the peak power times are between 12 and 5 p.m. So we will allow the battery to discharge during those times. And there are 6 hours there. And so let's just assume that we want to uniformly discharge over those 6 hours, which will be about 16% per hour of capacity. We'll assume that the weekend's not important. And so basically this period 1 is just going to allow the battery to charge from any excess PV. And so finally, we'll go ahead and click Simulate. And now let's go ahead and look at some summary economics. And so the net present value of the system is $12,000. So that indicates that this PV and battery system is economic. But the question is whether or not it's as good as it could be, or if the battery is actually providing value. And so let's take a look at what the demand charge without the system looks like, and then what the demand charge with the system looks like. And so you can see in the summer here, these little blue underlays, that would be the amount of demand charge reduction that the battery and PV system provided. And so in the other periods of the year, there's really not much. In the summer periods, there's maybe $500 per month. And so actually not really a lot, but we can see whether or not we can improve that. Let's also take a quick look at what power components are going to the load. And so the power to the electric load from the PV system, from the battery system, and then from the grid. We can zoom in here and then click on this little wrench, and we can do a stacked area plot. And you can see that we're really not providing a ton of battery power to the load, simply because the load is so large and our battery is kind of tiny in comparison. And so we're going to go ahead and modify our dispatch, modify our battery a bit. Before we change the size of the battery, I want to change from manual dispatch over to this peak shaving one-day look-ahead, which is more tailored to do demand charge reduction. The reason that a manual dispatch strategy really isn't going to be sufficient is that we can't predict ahead of time when the demand peaks are going to be, such that we can't really program a manual dispatch control ahead of time to do peak shaving. And so that's really what this controller is going to allow us to do. So if we go ahead and simulate here, it might be interesting again to look at how much demand charge reduction that we can achieve. And so the demand charge without the system, and then the demand charge with the system. And so we're really not getting a ton more here, but it really is just a function of the size of the battery at this point. And so is 10 kilowatt hours really the best size of battery for this particular site and PV array? Well, we can do some analysis that will show us what the most valuable size is. So I'm going to go ahead and do an approximation for an optimal sizing analysis of the battery size. Before I do that, I also want to point out this macro. So if you click on this macro area, there's a battery financials macro. And what this is going to do is break out the value of a battery system versus the PV system versus no system. And so the question might be, does adding a battery help or hurt the PV system? And so what this macro does is run the simulation with and without a battery, and then look at the project economics. And so you can see that with a PV system alone, we do have a net present value of about $15,000. And then with the PV plus battery, we have a net present value of about $18,000. And so in this particular case, the battery is providing some additional value to the system. But if we really want to try and find the battery system that's going to provide the most value, we can do a parametric analysis on the battery size. And so I clicked the parametrics button down here, and then quick setup. And then the variables that we want to look at are going to be within the battery section under desired bank capacity and then desired bank voltage. And then as outputs, we're going to want to look at the net present value. Which I believe I specify somewhere else. So under desired bank capacity, I want to look at sizes going all the way from 0 to 100. So basically, discrete battery units that we can install and look at how adding each of them provides less or more value. So if I click OK here, and then under battery bank voltage, if you will recall, one system has a nominal voltage of about 350 volts. So I'm going to increment by 350 volts. And I'm going to make these linked. So basically, as we change the bank capacity, we also change the bank voltage. And then under outputs, I'm going to add net present value. And before I run the simulation, basically anything that I'm not changing in this parametric table comes from the underlying model. So if you want to look at a parametric over a different dispatch strategy, you simply change it here and then go back to the parametrics. So we're going to be looking at the peak shaving look ahead. So let's go ahead and just run these simulations and see what kind of net present value we get. So it'll run on all of the processors that you have available. And you get this curve here of net present value. And so basically, as we increase the battery size from nothing up to 10 kilowatt hours over to 20, we get an increased net present value where we have perhaps 40 or 50 kilowatt hours. And then we start seeing declining returns as the capital costs begin to outweigh the benefit of offsetting additional electricity. And so while this is not actually doing a mathematical optimization, it is a pretty valuable approach towards looking at how changing various parameters of your system can provide value. And so with that, I will point out just a few more outputs that you can look at, and then we will move on to some questions. And so within the time series outputs, you can look at things like the battery state of charge. So how does the battery discharge over each hour? How does it charge? If we break this up into stepped lines, that will be over that time period. You can look at things like the battery capacity percent for lifetime, which is basically a measure of how the battery is degrading over time. And so I zoomed this all the way out over the whole 25 years. And so over the whole 25 years, as this battery cycles, it's losing capacity until at the end, it's only at about 30% capacity. And so our 10 kilowatt hour battery at the end of this simulation can only hold 3 kilowatt hours of capacity. And so you might want to start looking at things like Well, if I replace that battery at 70% capacity, how does that change my project? And so now you see that instead of replacing at 30% way out near the end of life, we're replacing sometime around 10 years, then sometime around 20 years. But that's going to cost money. So we have these large capital outlays during these times that we're going to have to evaluate if those make sense, if those provide, if the value that the batteries provide is worth these additional capital costs. And so there are a lot of questions that you can answer with this type of analysis with SAM. I hope I've begun to touch on some of the ways that you can program SAM and start to tackle these questions. But I'm sure that we have a bunch of questions, and so I'm going to go ahead and wrap it up for now and just point you as well to some additional resources about the technical features of this model, as well as an example case study similar to what I walked through today. And so if you have additional questions, I'd certainly point you there. And now I think I will open it up for questions. If my colleagues, Janine and Aaron, have been diligently answering them, and do you have any that are particularly interesting?
So one group of questions we got, there were a bunch on the load data. And so if you could maybe go back to the load page and show people a couple ways to enter it and where they can download some load data, I think that would address a group of the questions that have come in.
Sure. So electric load data is very important and somewhat hard to find depending on where you are. And so one resource that I have used is called the EnerNOC database. And so if I just open up, trying to remember where that is. So within the economic case study that I pointed you to, there is a link within there to the EnerNOC database, which is basically a commercial database, a commercial load database that has 5-minute load data. And so in the references here, there's this 2012 commercial energy consumption data that's available at this website. Okay. And so if you had that data, you can click Edit Data, change time step, and there's 5-minute data. So I actually have some of that load data available. Simply open the file, and basically you just have a list of load data. So this would be in kilowatts, and this is at 5-minute intervals. So I'd paste that there, click OK. And then you'd see this monthly load summary change. And then we also have this download electric load macro that will download an hourly load file from the OpenEI commercial load database and then directly import it. And so if you have a building that's similar to a small office, you could choose that over here and then click Run Macro, it will reach out to this OpenAI data set and go ahead and apply it. And so those are some options depending on whether you have custom load data or whether you want to use a representative building load.
Great, thanks. We have some questions about battery replacement. In the scheduled replacements, can you replace a battery with one that has a different capacity? Is the assumption that the battery has zero value at the end of life, and can you change that?
Those are excellent questions. Right now, the battery that you replace is identical to the one that you originally installed. So unfortunately, you don't have the flexibility to change the battery capacity when you replace it. And so the way you would enter the number of years, and then say at year 10, indicate 1 for battery replacement, year 20 for battery replacement. But then those batteries would just be the same battery capacity that you installed originally up here. And then as far as salvage value on batteries go, we don't currently value battery end of life. I think it would be a really interesting question, especially as batteries become, potentially more valuable for quick power, but not necessarily holding large amounts of capacity. So you'd have to add those values back in yourself, unfortunately.
There's one more question related to replacing batteries. Is there a way to escalate or de-escalate the cost of the battery for future use?
That's also a very good question, and yes, there is. If we assume that things like the Gigafactory are going to dramatically reduce the cost of batteries, we could say if our original installed cost is $600 per kilowatt hour in year 0, but we think that there's going to be just a major battery revolution, and it's going to reduce in price by 5% every year. We can go ahead and do that. And then you see, if you recall before, these spikes were a little more, I believe, and so they should be de-escalating. So yes, you can look at battery de-escalation, as well as if you are pessimistic on batteries and think that they're going to get more expensive, you can also model that. So.
Great. We had another question about modeling power leakage, meaning that does SAM assume that all the power that's used to charge the battery stays in the battery while it's sitting there not being used?
Also a good question, and we don't model power leakage. We basically assume that whatever capacity is stored is available from the perspective that it hasn't been lost parasitically. It is lost through the power converters, and then there is also the concept of basically just round-trip efficiency. So as the battery charges and discharges at different voltages, it might you might discharge a slightly lower power than you charged. However, we don't over time degrade the amount of capacity in the battery.
We had one question on the relationship between battery capacity and operating temperature. Maybe you could revisit that.
Sure. So, as many of you might, if you for instance, leave your cell phone in your car in the garage during the winter, and you come back in the morning and it's dead, that's because battery capacity is a function of temperature. And as it gets colder, battery capacity decreases. As it gets warmer, battery capacity increases. However, the degradation of the battery also increases as temperature increases. And so we basically have created a model that basically we're solving a differential equation to model the temperature of the battery over time as a function of the current flow through it and the size and physical properties of the battery. And so as this temperature changes, you can input this capacity curve that a lot of battery spec sheets have, and that will basically tell you if you're operating your battery down, at a very cold temperature, it's only going to have a certain amount of capacity available relative to if you're operating at a more standard operating temperature, say 25 C, then that's going to give you the rated capacity of the battery. And so it's just a way for us to help you model if you are operating these systems in environments that are perhaps not warm or have varying temperatures, it gives a more realistic capacity.
And I guess we probably have time for about one more question. There was a couple of questions on analyzing economic value. So if there's something that you could show for how to analyze the various financial metrics associated with PV plus battery systems.
Sure, yeah. I mean, of course, the most interesting part of batteries is whether or not they can make you money. So we've composed this macro that, again, helps you break out the cost, the benefits of installing a battery versus just PV or no system. And so if you click this Run Macro button, it will run the current scenario that is programmed, and it will run that for no system, for just the PV system, and then for the PV plus the battery system. And then that will elucidate the value or negative value of each. And so you can look at how the demand charges break out if there's PV plus battery, how the capital costs look. And so you can see here that in the PV only case, costs about $104,000. Adding battery adds another $15,000. And so at the end of the day, we're really just interested in the net present value over the life. And you can see that adding batteries actually makes it worse in this case. And so the PV system by itself is not economic, but the battery system makes it further uneconomic. And so this is one tool to help you evaluate your battery finance.
Great.
So yeah, it looks like we are just up against 2 o'clock, which is the end of our time. But I again would encourage you to visit our website, look at our technical reports, and if you have additional questions, you can post questions on the support forum, and we will follow up with you. So thank you again for attending the webinar, and we will provide additional announcements as we have more of these. So thank you again.